In fact, Engelbert Schucking once talked about this and said it's a little bit like in Maxwell's theory, if you had known only the Coulomb force had been tested and you said this predicts electromagnetic waves, there is a huge extrapolation from the static solutions in the solar system where we test general relativity to the dynamic solutions here. And the third point is there's an incredible extrapolation back in time to physical conditions which are totally different from the present day. Now, I believe the Einstein equations are true back at that time because they are so unbelievably unique. They're incredibly unique. But that is a huge extrapolation. So one way around all of this is to say it's all based on the Einstein equations, and who knows if the Einstein equations are true, A, on those scales, and B, at those times. Well, physics, we have to take what we know and extrapolate what we know, and so we have to take the Einstein equations because they're the best we've got. But I'm just saying, if you want to say what other ways are there out of the singularity theorem, one is to say, well, let's violate the energy condition, which we can do with scalar fields. And one is to say, I don't believe the Einstein field equations at those times or on those scales. Yes?
Isn't Holson-Taylor, the pulsar timing experiments, Holson-Taylor, isn't that enough to
it's very
dynamics?
Well, it's solar system scale.
Yeah, but it does produce an energy loss.
It's very weak dynamics. I mean, I agree.
It's dynamical.
It's dynamical at a very, very weak field limit. This is not a weak field limit. Okay, now, let's get on with the rest of this and talk now about the evolution of the universe. Okay, now we've got this field equation here, and there's a remarkable feature that happens. What I must remind you of, we have the energy equation, rho dot plus 3 A dot over A into rho plus P is naught, and a remarkable thing happens. Take this equation, multiply that by A dot squared times A, and integrate. Multiply this by A dot. And you can integrate it, given this equation, and you can integrate it to get the following equation. 3s dot squared minus kappa mu s squared minus lambda s squared is a constant. And that is a first integral of the other equations. And this is the famous Friedmann equation, the equation Friedmann discovered way back in 1922 for the case k is plus 1. Now, what you can do is spend a bit of time looking at that, and what you find is this constant is in fact the spatial curvature. Now, I don't have time to go into the details of that, which will be in these notes which I'm giving out to you, but I want to give you the canonical form of the Friedmann equation. 3s dot squared over s squared minus kappa mu minus lambda is equal to minus 3k over s squared. If you spend a bit of time doing Riemannian geometry, trying to examine this constant, you find this is that, where k is nothing other than this k here. And so what you get is really important different signs in this equation. This is the spatial curvature constant, which we've got up there, and that is the Friedmann equation, which we have to solve, which is the first integral of Ray-Choudhury. What that means is it's a first integral provided that you're expanding, and we now will leave the static universe behind. So what it means is what you have to solve in cosmology is these two equations. It's what you have to solve in cosmology is these two equations for the standard model. Now, this is indeterminate until you give an equation of state P is P of rho. Sorry, I keep on in my notes I've got a mu or a rho. You'll have to get used to mu and rho being interchangeable for the energy density. Okay, this is what we have to solve. So what we have to do, specify an equation of state, solve for the energy density, put the energy density into here, and then solve that equation. And so basically cosmology dynamically comes down to solving that equation. Now, the parameters is the Hubble constant, S dot over S naught. So the Hubble parameter, that's one of the parameters we get. Second important parameter is the deceleration parameter, minus 1 over h naught squared, S double dot over S 0. These factors are put in to make it dimensionless, and that is telling you the curvature of this curve. That is positive if it's bending down and negative if it's bending up. So that is a dimensionless form of the curvature, and the h naught is the slope. So h is the slope and q naught is the curvature of this curve. And then what we do here is we express the matter in terms of these parameters omega. Omega is kappa rho over 3h naught squared. And you can get that for the baryons. You can get it for the total matter. So for baryons, you will be the baryon density. For the total matter, it will be the total density. You can get a cosmological constant term, which is lambda over 3h naught squared. And the dimensionless versions of the energy density parameter is this for each component, for your photons, your neutrinos, your baryons, your cold dark matter, and so on. And the total energy density, omega naught, is the sum of those for all of these terms here. Okay. Now, what you can do is evaluate this equation today. Put on a 0 here. Now, today, the pressure is negligible. That's basically the deceleration parameter. That's basically your omega naught. So if you evaluate that today, what you get is q naught is a half omega of all the matter minus omega lambda. And that is the one equation relating these parameters. The deceleration of the universe is a half the omega of all the matter present minus the omega for the cosmological constant. The second one is that the curvature today, which is by definition k over a naught squared, is equal to h naught squared into omega m plus omega lambda minus 1. That's the present curvature today. And so if you can measure the amount of matter and the cosmological constant, this gives you the deceleration parameter. Or if you have the deceleration parameter, this will tell you the difference between the two. And then the spatial curvature comes out of that particular sum. Okay, if lambda is 0, if there's no cosmological constant, you get q naught is a half omega m, just that the deceleration of the universe is directly given by the amount of matter, and you get that the curvature, k over a naught squared, is equal to h naught squared into omega m minus 1. And you see that omega m is 1 is the critical value, because that is a flat space section. That is a flat space section if there's no cosmological constant. If it is greater than 1, we have k as plus 1, which I talked about yesterday, closed space sections. And if it is less than 1, we have k as minus 1, which is the hyperbolic case. So immediately you see, if we can get hold of this parameter omega m, and we know lambda is vanishing, we can find out the spatial curvature. It's a bit more complicated if the cosmological constant is non-zero, but this is what will tell you. Are the space sections flat, negatively curved, positively curved, what I talked about yesterday? It will immediately come out from this equation here. And the universe accelerating or decelerating relates these two. If it vanishes, you get these simplified relations. Throughout the 1960s, 70s, 80s, everybody assumed lambda was naught. So Alan Sandage published a famous paper called Cosmology, the Search for Two Numbers. And that was q naught and omega m he was talking about. Right. Now, what we need to do is look at the nature of the solutions. And, of course, they are... Let's just briefly look at lambda is naught and the solutions for ordinary matter. Lambda ordinary matter are very, very simple. You recollapse if k is plus 1. You are on the border. This is the scale factor as a function of time. If k is naught, and you expand forever if k is minus 1. Now that immediately follows from these equations here. And what I just want to point out here is the Friedmann equation. A turning point of the Friedmann equation happens when S dot is naught. When is S dot is naught? It's when, I must make sure I get the signs correct in this one. It's when kappa mu plus lambda is equal to 3k over S squared. That's when a turning point happens. And so if there's no cosmological constant, you need kappa mu is 3k over S squared. And so that immediately tells you you can only get this if k is positive. The only times that solutions turn around, maxima or minima, is if they are positively spatially curved. Now, this is something which some cosmologists have forgotten nowadays. Any interesting behavior, if you have vanishing lambda, can only happen, in fact, and with the normal lambda, for most people assume lambda is positive. So if you have a positive lambda, if you have positive matter, which all ordinary matter is, the only interesting cases in terms of turning around, if you want a minimum, if you want to avoid the singularity, not only if you want to avoid the singularity, must you avoid this condition, you must also have positive spatial curvature in order to get interesting behavior. So the turnaround happens for positive curvature, and that happens for the critical density, for critical density greater than 1, here critical density equals 1, here critical density less than 1. That's for vanishing cosmological constant. Now, for lambda positive, all sorts of other behaviors are possible because you can get the Einstein static universe. And I should say that this applies to Einstein static. Einstein static must have k as plus 1 for exactly the reason I've said. And that was the reason Einstein liked the Einstein static universe. He wanted closed space sections. Now, why did Einstein want closed space sections? Because he spent a lot of time worrying about the boundary conditions for physics at infinity. And he said to himself, if the universe space sections close up, there isn't an infinity, so there are no problems of boundary conditions at infinity. You've heard echoes of this in the Hartle-Hawking no boundary conditions for the universe story. Einstein was there in 1917. When he found his cosmological model, actually he wasn't trying to solve cosmology, he was trying to solve Mach's principle and boundary conditions for local physics. And that's where he got this model from, really. And so the point about it is, for k is plus 1, for the Einstein static model, must have k as plus 1. You can get models which are asymptotic to it, which collapse. You can get models asymptotic to it, which expand. You can get models which are non-singular like that. You can get Big Bang models like that. You can get Big Bang models which recollapse. All of these behaviors are possible when the cosmological constant is positive. All of the interesting ones I've just pointed out occur only if k is plus 1. So this must have k is plus 1. This must have k is plus 1. This must have k is plus 1. Right. Now, we can get some exact solutions, which I'm not going to write down, except I'm just going to say there are 3 important simplest solutions, and it's important to know the simplest solutions in cosmology. And they all have names. And the first one is the Einstein de Sitter universe, which is, ask yourself, what is the simplest solution I can get of these equations? Well, the simplest solution is if I put the pressure to 0, the cosmological constant to 0, and the curvature to 0. That's my simplest solution. Well, it then becomes pretty easy to solve because that term is gone and that term is gone. You've just got those two. And this equation is solved for p is naught. We get the density is a constant over s cubed. So you put that in there, missing those two, and you easily find the scale factor is proportional to t to the 2/3. And most astrophysicists use that model as a background when they're doing astrophysics because it's a pretty good model of the universe since the time of decoupling of matter and radiation. You want to have a background for formation of galaxies, structure, and so on. That's the model people use because it's the simplest one you can get. Okay, that's the Einstein de Sitter universe. And incidentally, the age of this universe is 2/3 1 over h naught, which easily follows. So if you remember here, your limit on the age was 1 over h naught. Well, the Einstein de Sitter model comes in as 2/3 of that value. 2/3 of that value. Okay, now, the next one is the Milne universe. And the Milne universe comes in with P is naught, and the energy density is naught, and lambda is naught, and K is -1. And that's a bit strange because this is now an empty universe.